You know all that software we use every single day, from media players to the editors we write in? Well, it's all got hidden flaws, and there's this constant race to find those flaws before the bad guys do. Today, we're going to dive into a really fascinating technique for doing just that. It's called smart fuzzing, and it's a super clever approach that's all about finding bugs by thinking, not just by randomly breaking things. So, let's get into it.
Okay, so let's start with a simple question. Let's say I hand you a video file. You're a security researcher, and you have a hunch there's a really nasty bug hidden deep inside the program that plays it. How would you actually find it? You're probably thinking it involves some kind of super complex surgical analysis, right?
Well, the standard method is, believe it or not, surprisingly crude. Most of the time you find these bugs by just randomly scrambling the file's data. Yeah, literally just flipping bits from 0 to 1, deleting random chunks of it, adding digital noise, and then you just throw these broken files at the program millions of times, just waiting for it to crash. It's a total brute force approach, and it's got one heck of a problem.
So let's take a closer look at this breaking things method. In the cybersecurity world, this whole process has a pretty cool name: fuzzing.
So here's the official definition for you. Fuzzing is all about automation. You have a tool, it's called a fuzzer, and it just bombards a program with millions and millions of messed up inputs. It's hunting for that one single magic combination that reveals a weakness. It's a numbers game, and don't get me wrong, it's been super successful, but it has a massive blind spot.
And this right here shows the core weakness of what we often call dumb fuzzing. See, when you give a program a valid, properly structured file, it gets parsed correctly, and all the deep, complex logic of the program kicks in. But when you feed it a randomly scrambled file, the program's parser usually takes one look, says, "Nope, this is garbage," and rejects it on the spot. Your test never even gets past the front door.
And that's the real problem, isn't it? All the interesting, complex, and potentially dangerous code is hiding behind that initial check. If your fuzzer can't generate inputs that are at least valid enough to get past that first guard, it just ends up testing the same shallow error-handling code over and over and over again. Meanwhile, the real juicy vulnerabilities, they remain completely untouched.
Okay, to make this crystal clear, let's look at a real-world bug that traditional fuzzing just could not find. This story really illustrates the problem perfectly. So the target was something called the WavePak audio library. Now, you probably never heard of WavePak, but I guarantee you've used it. It's built into tons of popular software like VLC Media Player, Winamp, even Adobe Audition. And researchers found a critical vulnerability in it, one that could literally let an attacker take over your computer just by getting you to open a malicious audio file. Pretty scary stuff.
So what was the secret? Well, a normal WAV audio file has a very strict structure, and it's made up of sections called chunks. It's supposed to have exactly one of these chunks, a format chunk, that tells the player all the audio details. The vulnerability was only triggered by a file that was cleverly crafted to have two of these format chunks. Think about it. A random bit flipper is almost never going to accidentally create something that specific.
Let's break down how this brilliant little exploit works. First, the attacker's file presents a totally normal, safe-looking format chunk. The audio player reads it, runs all its safety checks, and goes, "Yep, everything looks good here." But then, here comes the secret weapon, a second format chunk snuck in right after the first. This chunk overwrites some of the key values from the first one, tricking the program into a weird, invalid state that all those initial safety checks completely missed. And the result? A program crash and a wide-open door for an attacker.
And look, don't just take my word for it. This quote from the research paper that discovered this method really sums it up perfectly. They said the odds of a traditional fuzzer, like the famous one called AFL, randomly flipping bits in just the right sequence to manufacture an entire, valid second format chunk were extremely unlikely. Basically, it was never going to happen.
So if blindly breaking things doesn't work for these really complex bugs, what's the alternative? This is where the research gets really interesting. It's time to give the fuzzer a brain.
So the question becomes, how could you design a fuzzer that's actually smart enough to understand the structure of a WAV file and then intelligently construct that malicious two-chunk file all by itself?
And here is the answer, a technique called smart Greybox fuzzing. The key idea here is to actually teach the fuzzer the rules of the file format. So instead of seeing a file as just a long string of ones and zeros, it learns to see it as a collection of meaningful parts, chunks, attributes, relationships, pretty much the same way a human programmer would.
This is what makes it a gray box technique. It's kind of the best of both worlds.
It has the structure awareness of a really smart fuzzer that understands the file's grammar, but it also keeps the coverage feedback from a traditional fuzzer, and that feedback is crucial. It tells the fuzzer which of its intelligent changes are actually exploring new and interesting parts of the program's code, so it can learn and get even smarter over time.
Okay, so that's the high-level concept. It sounds pretty cool, right? But how does it actually work under the hood?
The whole process starts by taking a valid file and a file format specification, basically a rulebook. It parses that file to create this incredibly detailed map, what it calls a virtual structure. It identifies every single chunk. You can see the parent and children elements here, and it notes its type, where it starts and ends, and how it relates to everything else. It's basically building a complete structural blueprint of the file.
And once it has this blueprint, the fuzzer unlocks a whole new set of what you could call superpowers. It calls them smart mutations. Instead of just flipping random bits, it can perform surgery. It can intelligently delete an entire valid chunk. It can do a smart addition, grabbing a chunk from a completely different file and inserting it. Or it can do a smart splice, replacing one chunk with another valid chunk of the same type. It's incredibly powerful.
You know, there's a fantastic analogy to help understand the difference here. Dumb fuzzing? That's like trying to edit a novel by changing random letters. You're almost always going to end up with meaningless gibberish. But smart fuzzing, that's like swapping entire paragraphs, or even whole chapters. The result is still a valid, readable story, but it's a new story that tests the reader, the program, in a completely different and more profound way.
Okay, so the theory is really impressive. But did it actually work in the real world? Come on, let's look at the results. Get this. 42. The tool the researchers built, called AFLSMART, discovered 42 previously unknown zero-day vulnerabilities in widely used, well-tested software. These are major bugs in programs people are relying on every single day. That's a huge number. And the leap in performance is just wow. They did a head-to-head 24-hour test. The traditional fuzzer, AFL, found 16 bugs. Now that's a pretty good result on its own. But AFLSMART, using its intelligent, structure-aware approach, found 33. It was more than twice as effective in the exact same amount of time. It's not even close.
And it wasn't just about finding more crashes. It did a much better job of actually exploring the programs. It achieved up to an 87% improvement in something called code coverage. All that means is that its intelligently crafted files were successfully getting past those front door guards and testing huge areas of complex code that the dumb fuzzers simply could not reach.
So the crucial takeaway here is that this much smarter approach found dozens of serious bugs in software that we already thought was secure, software that had already been well fuzzed. And that leaves us with a pretty compelling final question, one that might just keep you up at night. If this technique can uncover so many hidden flaws in programs we thought were safe, what else is still hiding in the apps you and I use every single day?